Hi, Jacobus. Yes.
Okay, so does it work?
Yeah.
Okay. These are my collaborators. Most of the work was done in collaboration with Antonio Garcia, who's actually the neighborhood of Korea, Shanghai. With Dario, we wrote, I think, 5 or so papers, maybe more. I didn't really count them today. I have a number of students. Yang is a student of mine. He's at the Weizmann Institute. He's an excellent student. Also, Lucas Sa is here. He's going to Cambridge University in the UK. Yiping is going to Beijing at COS. This is my current student. Perhaps you have heard of Martin Zernbauer, some of you. And we together wrote the first paper on SYK. The first paper I wrote on SYK was together with Martin already in 1984, long before the SYK model was named SYK model. Okay, so the papers I discuss today are mostly on this paper with the title Keldysh wormhole and anomalous relaxation in the dissipative SYK model. Keldysh is an ingredient, it's not very important. I will actually not discuss the Keldysh technique. Anomalous relaxation is important, and there's dissipation. So the anomalous means that there's much more dissipation than we would expect.
No, it's lower than it needs a time after pressing the button.
Yeah. Okay, so I will start out with the introduction, introduce how chaos enters in the SYK model, and discuss the dissipative model and how we solve that. We did it in 3 different ways. At large n, where we used Schwinger-Dyson equation, also the Keldysh formalism, and at finite n by exact diagonalization. We got some puzzling results, And that is why we looked at the two-body interaction, where we can do everything analytically. And if there's still time, which I don't think there is, I will discuss something which is called the dissipative form factor. So please feel free to interrupt me at any time. I have all the time, and I don't have to finish at 5. This thing doesn't work.
Now it's
working. Yeah, it's
a diffusive process.
Yes. So I start with an introduction of the SYK model. Okay, I don't need this thing. Does this work? No, this blue. Okay. Yeah. Okay. So the SYK model is a many-body problem, and here there's a 4-body interaction. The chi's are fermions. They are Majorana fermions, and that means that they are linear combinations of fermionic creation and annihilation operators, as I wrote down here. They anti-commute. This you can get from the standard fermionic commutation relations. The chi's are element because of this relation of a Lindblad algebra. That means they have the same commutation relations as gamma matrices. In this case, because there are n of them, they are gamma matrices in n dimensions. So that means that the chi's are very large matrices of 2 to the power n over 2 times 2 to the power n over 2. And if you study this model at finite n, you just work with these very large matrices and just multiply them and do whatever you do with the large matrices. And the simplification is that these are gamma matrices, and that is why they are tensor products of polyspin matrices. And that greatly simplifies the construction of this Hamiltonian. Also, not in the least, because of the tensor product structure, they are very sparse, the matrices. So you have only a very small number of non-zero elements, like 1 element per row and column. These are random numbers, typically taken constantly distributed with some scaling in this way, so that the ground state energy of this Hamiltonian scales with n, which makes it kind of physical. That's what you expect. If you have n particles, the ground state energy should be should scale with n. This model is called the Sachdev-Ye-Kitaev model. It was invented, I would say, by modern French in 1975. A precursor of the model was invented by Boigas and Flores and French and Wang. And Sachdev-Ye invented another precursor of the Sachdev-Ye-Kitaev model, which is actually quite different from the Sachdev-Ye-Kitaev model. It was invented in nuclear physics, and the reason was that it was well known that in nuclei, the nuclear levels were correlated according to random matrix theory. That was already known by Wigner in 1955. However, the nuclear level density goes up exponentially. Whereas in random matrix theory, you always find the semicircle, which was not at all the right result. And that made people think, why is there, what is the source of this completely wrong level density? And because the nuclear interaction is a two-body interaction, or four-body, depending on how you name it, the idea was that this was an important thing that was missing in this model. And that is why Boigas, Flores, French, and Wong introduced this ensemble. And they indeed found it still had the same level correlations, but that the level density in their analysis, it went up like a Gaussian. In a more recent analysis by Kitaev, it actually was found it goes up as an exponential of a square root, which is exactly what was found already by Bethe in 1935 for the nuclear level density. The model which Sachdev introduced was kind of a spin class model, where he had SUN matrices, these Si and Sj, which you can represent in terms of fermionic creation and annihilation operator. So it's really a spin model. It's quite different from the SYK. The model on the previous slide was introduced by Kitaev. And what he wanted to do is just before this model was introduced, these guys introduced a result that showed that there's an upper bound to the Lyapunov exponent. However, at that time, there were no models that saturated this upper bound. And Kitaev actually found that his model, the model of the previous slide, saturates this upper bound. And that really created a lot of excitement in this field, because it was long believed, and I don't know exactly why, that black holes also saturate the upper bound. Another important property of SYK model is that the entropy of the ground state is extensive. It scales with the number of particles. Yeah.
So I mean, that is the ground state is highly degenerate. The ground state is highly degenerate.
No, it's not degenerate. Almost.
I mean, the idea is that the density of state very close to the ground state is a hard bound, a little bit like Wigner. So you have an enormous amount of states very close to the ground states, and they contribute to the zero temperature entropy.
Yeah, it's a matter of taking limits, because the level spacing also near the ground state is exponentially large. So they all separate. They are all non-degenerate. They are a finite distance apart, but the distance becomes exponentially small, like 2 to the power minus n over 4.
It becomes smaller than the typical level spacing.
No. The typical level spacing is also very small, but it becomes small in comparison to the number of particles. If you take the problem is when you have a many-body Hilbert space, you have two scales, two large things. And one is the number of particles that goes to infinity. The second much larger thing is the number of states in the Hilbert space. And the number of states in the Hilbert space is 2 to the power n. It's much larger, and the spacing of the level is 1 divided by 2 to the power n.
Indeed, when people talk about the low temperature entropy, the zero temperature, they always have in mind the limit in which beta goes to infinite, but much slower than n goes to infinity. Such that, yeah.
Is there any difference instead of, because here I think JF, well, Gaussian rounded variables. If I take binary,
Doesn't matter.
even to the ground state.
For the ground state, basically doesn't matter. But you may have to do, binary doesn't matter at all. You can do much more radical things. And that is what we did with Dario. You can take that matrix, a big matrix, and there are matrix elements, the W, alpha, beta, gamma, delta. They're of order n to the power of 4 of them. And so say n is 10, you have 10,000 of them. And then we say, of those 10,000, we make 9,990 equal to 0 at random. And we keep only 10 non-zero. and that doesn't change the properties of the model.
Yeah, I remember.
So there's a very strong universality. You can make, so the distribution is completely irrelevant in that sense, which in essence what you mean by universality.
Well, sorry, still asking, has this been checked very? This distribution doesn't matter.
Oh yeah, in that sense, in that paper with Dario, we checked that. We looked at many different things. There are analytical arguments. More recently, and that's not published, we calculate the OTOC. OTOC is the same. That doesn't matter. There are some you have to rescale things in a correct way. Because you have far fewer non-zero matrix elements, the strength of the couplings you have to scale up. Otherwise, you cannot get this. Okay. No, okay. I have to go this way.
Sorry, may I ask also a question? When you introduce about the next slide,
Okay.
There is a representation of SI spin, and on the right hand side, I can't find I. Could you please comment?
On the right hand side?
Yes, SI mu is equal to some sum of what I are.
Oh, yeah. Yeah, I say that this sum shouldn't be here.
No, shouldn't there be? I think it should be and then the matrix S. If I remember correctly, shouldn't there be dagger than the matrix S?
No, there's some typo. You can make these are generators of SU, and you can make them out of creation and annihilation operators. So these indices should be correct. I think there's something wrong with this sum. Thank you. Didn't notice that. So another SYK model, which we also looked at with Dario and Antonio, and that also comes up in a dissipative SYK model, and that is a coupled SYK model. So you have the left SYK model, the right SYK model, which actually have the same couplings. The right fermions know about the left fermions in the sense that they anti-commute, but nothing else. And there's an explicit coupling term, and which was introduced by Madasena and Chi. The nice thing about this model is that the ground state is gapped. It has a gap, which is relatively Dissipative Sachdev-Ye-Kitaev. So the ground state is below the state when there's no coupling. When there's no coupling, this is just two non-interacting skirmion models, SYK models, with the ground energy, state energy, which is given by twice the ground state energy of a single SYK model. In gravity, this is interpreted as two black holes in some sense, whereas this has a low energy below that of two black holes, so it's a wormhole solution by definition. Don't mention the name. The ground state also it has a gap, the first excited state, which is large in the sense that it goes like a power of this coupling, which is below 1. You have a question? Yeah.
Why not consider the coupling? Why the quadratic coupling and not one? Because in principle, also instead just add just the or term with 2 L's, 2 R's.
Oh yeah. No, this is simple term. We looked at the square of this term, and you can look at any power of this term.
Right.
So the properties are different if you look at different couplings, but this one is the simple stair one. So, but you can look at other terms. There are other couplings on the market people looked, I think, Igor Klebanov has another coupling. So there are other possibilities. So let's now look at chaos in the SYK model. I will discuss two things and to measure chaos. One is spectral form factor, and the other one is the out of time order correlator. So how do you measure chaos? We know that for a long time, in fact, since the work of Michael Berry, that and Boitas and collaborators, that you know that the system, if a system is chaotic, if the eigenvalues of the corresponding quantum system are related according to random matrix theory. And you can test that in several ways. One is just look at the spacing of the levels. Another one is if you have level sequence, you can look at the variance of the number in a given interval. And today I look at the spectral form factor, which is in fact the same as the number variance. Both observables follow from 2-point correlations. This is a Fourier transform, and this is another integral transform. I also discussed out of time order correlator, which is directly related to the quantum evolution. So there are some important time scales. One is the Lyapunov time, how fast trajectories diverge. Second one is the Ehrenfest time. So if you have exponential divergence of trajectories, as you can look at the time scale when the quantum noise becomes of the size of the system. And that's the Ehrenfest time. In this case, log n is the size of the system. There's the Thouless time. That is the time scale below which, this is the time scale beyond which eigenvalue correlations are given by random matrix theory. And there's a Heisenberg time, which is the largest time, which is the time scale of the inverse level spacing.
For systems, I never properly understood. For systems that don't have a classical analog, the Lyapunov time, how you
can calculate OTOC.
No, that I know, but
Yeah.
does it have an intrinsic meaning?
No, then that's harder to interpret.
Right.
If you,
Okay.
there are systems that do not have a vertical limit. So the spectral form factor is if you have eigenvalues K and L, it is just this Fourier transform. In fact, if you write it in terms of a 2-point correlation function, it's the Fourier transform of the 2-point correlation function. And it has a very simple form for a random matrix theory of complex Hermitian matrices, which is called GUE. It goes up linear up to this time, which is the Heisenberg time, and then it is constant. I also put in a second curve. And what you can do is the level density of the Gaussian unitary ensemble is a semicircle, like that. And you can fold in the level density in the spectral form factor. That means that you assume locally that you have this many levels according to this spacing, and you fold that into the form factor. And then you get this result. So that means this result is when the spacing of the levels is all exactly the same. It is all one or all constant. In this case, the levels are as in the semicircle. So you actually get a deviation from the GOE, but you fold in the level density of the system. And that has an advantage because if you look at numerical data, one thing, in order to find agreement with the GUEs, you have to unfold. You have to map the levels to constant spacing, to a sequence of constant spacing. And if you fold in the average level density, as I did here, you don't have to do that. And that means you can directly compare to the raw data. And you don't have to do much cooking. There are three important ensembles, in fact there are more, where this is the GUE. You can also have real symmetric matrices that it looks like this, or you can have quaternion matrices, and that the form factor has a singularity. This also has a singularity, and in this case, the derivative of this curve has a singularity, so you don't see that when you plot a graph.
May I ask a question? I'm not very familiar with the step of singularity. What does it mean physically?
There's some absolute value. What it means, it has a meaning. It is when you. It means if you do a perturbative calculation, at some point it will break down. It's important when you do a semi-classical analysis, you find that you cannot get to the plateau. So here you see two figures of the spectral form factor. This one was calculated here not too long ago. And here you did not do unfolding.
No, we did unfolding.
You did unfolding.
Yes. We didn't separate, we didn't remove the disconnect.
Oh, this is, okay, so I missed, okay. So the difference between these two curves is this one contains the disconnected part, which is very large. That is, this goes up to probably to 10,000, no, not 10,000, I think 10,000.
Yes.
And this is one. In this case, this is one. And here, this big contribution, which is due to the square of the level density, has been subtracted here. And the remarkable thing is that the agreement with the GOE is really very, very good. It is here that the curve is quite thick, and you don't see that. Here, intentionally, I made the curve very thin. To see that the agreement is 0.1%. And there is some cooking going in. There's a W here. That means I filter out some noise. The noise I filter out is because you have the spectrum as a whole. It does more or less this, going from realization to realization. And that is what I filtered down. Other filtering out because you do a Fourier transform. If you do a Fourier transform and there are edges, you get always a lot of junk from the edges. So you have to throw out the edges.
So how do you filter out the noise?
With a Gaussian.
Okay.
I think we also did that.
Yeah, and also with subtracting the oscillating part from the fluctuating part of the spectral density, I guess there's a similar to this one.
That could be. I didn't. Yeah. I did only Gaussian filtering.
Okay.
And this is a large. This is quite wide.
Yeah.
Which you have to do. However, people never trust if you cook the data. People don't trust what you are doing. So it is nice to actually not do that, to just plot the raw data. And that is why I discussed the folding in. Mm-hmm. Here you see again the curve that fluctuates. That's again an SYK model. And these are just raw data. That means that the spectral form factor is calculated from the raw eigenvalues, e to the power it, lambda k minus lambda l. And I folded in the analytical curve, the red curve, the spectral density, which is the analytical formula, here and here. So what I put in this curve, in the red curve, is n and 4. These are the only two numbers I put in. And the ground state energy, E0. And then you find perfect agreement within the noise of the levels. And this was for n equal to 26, where you have 4096 levels. So the out of time order correlator measures the Lyapunov exponent, which is the divergence of trajectories classically. So there's a small difference at time zero that increases exponentially with the Lyapunov exponent to the position or the trajectory at time t. And this evolution you can write in terms of Poisson brackets of qt and p0. And quantum mechanically, this becomes a commutator. And if you square this, that means you look at this quantity squared. So you have the square of the commutator, and then you have 4 different terms. And in 2 of those 4 terms, the time is out of order. And in 2, it is not. These terms are not interesting. They don't give a large contribution. But this term starts out decreasing exponentially. So, and for time scales which are below the Ehrenfest time, when the classical motion follows the quantum motion or vice versa, this should behave as this exponent. It is only for a short time because the Ehrenfest time is a very short time. So this exponent exists, is only visible for a short time. For the SYK model, what you calculate is the square of the commutator. So you have 2 operators, which are fermions, like the fermion, the gamma matrices at 2 different times. And you only calculate the out of time order 1, weighted by a Boltzmann factor. And technically, you have to distribute the Boltzmann factor over 4 different positions, or 2, and you just do the Heisenberg evolution of this operator. These are big matrices, gamma matrices, the fermions I had, and you just can evaluate this numerically. And the remarkable thing is that if you calculate the exponent, and that was done exponentially, it was done analytically by Maldacena and Stanford and Kitaev, they found that at low temperature, when beta is large, the Lyapunov exponent saturates this bound. And at lower temperatures, it is well below this bound. So it never goes above this bound. It is very hard to calculate this Lyapunov exponent exponentially. And the best published calculations you see in this figure, where you see the out of time order correlator as a function of time obtained by these authors. And these curves are from n equal to 12 to n equal to 60, which is a really large 60 fermions. And if you look at these curves, they are not exponential. They should go as 1 minus e to the power lambda t. And they don't do that. You cannot fit an exponential to these curves. It won't work. So it is very hard to extract an exponential behavior. Here I have a small n. And this one is fitted by kind of a Padet-like fit. It works, but you need 3 parameters to the fit seems to work reasonably well. And it gives a Lyapunov exponent of 0.5 for beta equal to 10. So it is less than 0.6. It is close to the bound. It's kind of what it should be. But the real problem is you cannot plot this on a log scale to see the exponent. You don't do. And these authors went to great length to basically still get out the exponent. But it is very, very hard. And the reason really is that the Ehrenfest time is very short. And you would need exponentially large values of n to actually see the exponential behavior. So let's now, unless there are questions. So let's now move to dissipation. I will use Lindblad evolution and solve the Lindblad equations using vectorization. I'll discuss Green's functions and the spectrum. Dissipation. So what's the idea of the Lindblad evolution? So the Lindblad evolution describes a system coupled to a environment, coupled in a Markovian way. It has no memory. And you rewrite the equations so that it only involves the density matrix of the system. The environment is completely integrated out. And the only remnant of the environment, this is the equilibrium evolution when there's no dissipation. And the only thing of the environment are these operators, which are called jump operators. And this kind of evolution I want to describe, and I want to study equilibration of this system when this is an SYK Hamiltonian, and these operators represent adding particles to the system. And for these operators, I use these fermionic operators. I add a Majorano particle to the system and study how the density matrix evolves. What you also see is that for these operators, which are Hermitian, and they square to 1, the identity operator, if the density matrix is the identity, of course, this vanishes. If this is the identity, you can commute it out, and when the square of this is equal to 1, and this is also the identity, so it is 0. And that means that the identity is the solution of this equation. So the identity solves this equation. The identity operator, typically you think of, that is the high temperature limit. And that's kind of what you expect. If you keep adding particles to the system with these operators, you equilibrate to a high temperature limit. The explicit equation we consider for the density matrix, which you can expand as an operator, bracket notation, is given by this equation. And I now wrote out the jump operators explicitly. The way to analyze this model is to vectorize the density matrix. That means, what it means is you have a matrix, and vectorizing means that you put all the columns of the matrix behind each other and make one big vector out of it. In bracket notation, it's very simple. So this is the operator, and you flip the bra to cat here, and then it becomes a vector. So this is the tensor product of two states. So if this acts in space V, then this is a vector in V cross V. The identity becomes particularly simple. This is the identity operator. If you flip this one, it becomes this state where the bra, these two cases are the same. And this is a famous state in the literature. This is called the thermal field double state, and that plays an important role in the analysis. It is a little bit more tricky to do, because one thing you have to do is so-called operator reflection. So if you have a gamma matrix or fermion, and this one acts only on this part of the tensor space, then there's a sum of a k, then this is equal to another operator adding on the right particle. This you can do, and you can imagine that this works if this is a complete, if gamma L times k is a complete set of states, and you rename that. if you rename gamma L times K, you name P, and then you get another gamma acting on the second one. That is kind of how it works. And that is an important ingredient. And this works in a particular representation of the gamma matrices, which is not really important for now. So the idea is that if you have, this is the Lindblad operator, it acts on the density matrix. And if you do that, then so here did I write too many brackets?
Yeah.
Yeah. So this bracket shouldn't be there. So this is the operator, because here's a bra and here's a cat, and this is the matrix element. Now I can do the vectorization. I can flip this, and I put this here, and I use complete, so I can sum over n, and then I get, because this one is flipped, I get this L row acting on these two. There's a sum over J. So this is again the thermal field double state. So what I should understand is how this L row act on this state. If I do that, then I know how this vectorized operator looks like. And like we wrote it out, how it works for one term. So that is this term. And so here I have the vectorized state, but now I put this one after the I. I use completeness. I get rid of the I, and I have two J's. So I act with gamma L, rho, gamma L. I act on two J's. Then this one acts on the left. I use operator reflection to make it act on the right, and I get a minus sign. So that means that this is equal to that. And then I insert completeness a couple of times. I insert completeness here. I insert completeness here, and I insert completeness here. And I do that in these two lines. And if you do that and you reorder it, what you find is here is the density matrix. These two combined that gives the vectorized density matrix. And what comes out is a new state, the MK state, where this one, gamma R, acts on the right state, and this one acts on the left state. So that means that this operator actually becomes the following operator, becomes the tensor product of a left gamma matrices and a right gamma matrices. So it's actually non-trivial how to get that correctly. So the operator we are studying in a vectorized language, and that is known in the quantum information literature as the Shor-Yam-Minkowski transformation. I don't know why they have to give it a name, because it's a completely trivial transformation. And this operator now looks as follows. So there's a left SYK model, there's a right SYK model, there's a minus sign. This looks exactly like the Mother-Sinner-Shi model, which we discussed before. And this is just a constant, so that doesn't matter. In comparison to the Mother-Sinner-Shi model, the difference is this term is actually the same. But here you get a plus sign, and here is a minus sign. And importantly, here there's an I. So that means this is actually a non-Hermitian operator. And that's kind of what you expect. You describe dissipation. You expect a non-Hermitian Hamiltonian, whereas this Hamiltonian is Hermitian. What you also see is that if you have a state KK, that means that the left and the right state is the same, then this one gives the same energy as this one, So that means that when this acts on kk, you get 0. If you sum over all of them, it is also an eigenstate of this one. It actually gives the ground state of this one. So that means we know the exact ground state of this Hamiltonian, and it is exactly the thermal field double state.
Wait, but there might be, no? Am I wrong? Can you go back? Because definitely kk is the ground state for the spin operator, so
Yeah.
for psi. It is a 0 energy state for that combination, but there might be states with more negative energy, no? So the
No.
fact. What?
No, that's the ground state.
But why?
The ground state, because of this constant, is exactly 0 ground state energy. And I have a picture of the spectrum. Maybe here. So this is how the spectrum looks like. This is the ground state energy. Z0. And if there's a first excited state, which is different by form u. And there are many complex eigenvalues there here. So this is an actual spectrum. So this is the ground state energy. This is form u. And then there are many complex eigenvalues. And these are actually the eigenvalues of the spin operator, which I put in there for comparison, which are space-time u. So that's mu is form u. And okay, so I have to skip this. So what we want to calculate is the Green's functions. We want to see how what is the gap, how fast the system relaxes. And we calculate them in 3 different ways. One is,
Well, this is not exactly related to this model, but I think there was also a proposal of the Lindbladian SYK.
which SYK?
Lindbladian, I think probably the jump operators were randomized.
Okay, that's basically the same. We also call this the Lindbladian SYK model.
Yeah, sure. But yeah, I was just wondering how does it compare to
It's the same. I would say it's the same.
It's either frozen or
And there's one of our collaborators, Lucas, wrote a paper about that, also Ryu and collaborators. So what you can do is you can choose the coupling term that is this term, and you can choose it differently. Posen and company, they looked at a quadratic term. There's Ryu and collaborators. They both looked at a quadratic term and at this term.
So I have a question. In the previous eigenvalues of the Euclidean.
Yeah.
So if we don't have that middle eigenvalue, can you comment on that? What is the difference, like the relaxation with respect to the relaxation time? So
Yeah. So the relaxation time. What the normal thing is, you have the ground state and the first excited state. And at large time, Green's functions will behave as Euclidean Green's functions will behave as e to the power minus the time times E0 minus E1.
okay. So without mu, you have the larger gap, and with mu, you have the.
Even without mu, when mu is 0, we have a large gap.
Yeah, and okay, and I'm just trying to understand the importance of mu or the additional eigenvalue in between the excited and 0.
You would think, I will come to that.
Okay.
You would think it is important, but it's actually not so. So we calculate the Green's function in 3 different ways. There's a Keldysh formalism where you put the left contour just below the real axis and the right contour just above the real axis. We did it in Euclidean space-time, going to 0 temperature, but then we changed the sign of the Hamiltonian. So 0 temperature is mapped to infinite temperature. And we did exact numerical calculation at finite end. The results of these two are identical, the same. This is actually not identical, and I will also comment on that. So let's now look at some results at the Green's functions and how they compare to solutions of the Schwinger-Dyson equations. So at finite n, the Green's functions are in Euclidean time are evolved in this way. Now the time is Euclidean, there's no I here, and there's a Boltzmann factor. And we calculate that in the low temperature limit. In the low temperature limit, because of the Boltzmann factor, this trace is just the ground state energy, and also 1 over c becomes e to the power minus beta E0. So what you have to evaluate is you do an intermediate state expansion here. It's just this evolution factor sandwiched between the left and right fermion. And if you put in a complete set, then for the ground state, this becomes some constant, maybe 1/2 or so. And the next state, the first excited state, this becomes E1. So this goes like e to the power minus tau times E1 minus E0, and this is larger than E0. And that is how you would expect how the Green's function relaxes. In our case, this difference is 4 mu. So what we would expect that this goes like e to the power of 4 mu times tau. And if you do a calculation, okay, I have here the spectrum, I already showed you that. So this energy difference is 4 mu. And if you look at the Green's function, that's now this the Euclidean Green's function. And what we find is, we find this tail, this curve is e to the power minus 4 mu tau, which is very nice. But we also see a second exponent, an early exponent, which is actually much larger. But this second excited state is very close to the first one. So in fact, looking at the spectrum, this one does not exist. If you plot the exponents, I plot now this exponent as a function of mu and this exponent. So this is the long tail. That behaves like this, and this curve is for mu. For small mu, it goes like mu, and for large mu, this is just proportional to mu, because then only the mu term dominates. If you look at the second curve, that is this slope, is actually interesting, because for large mu, it is basically the same. It should be perturbatively, and then it goes up. So you get stronger dissipation when you decrease the coupling. And then there seems to be a phase transition. And then you make mu equal to 0, and the dissipation doesn't go away. There's still dissipation if there's no coupling. And the question is, do we believe that? Do we make a mistake? That was my first reaction. And to understand what's going on, we did 2 things. We solved the Schwinger-Dyson equation to see what results we are getting. And we also looked at q equal to 2, this q equal to 4. And for q equal to 2 is integrable, where we can do everything analytically. Whether we can reproduce this behavior. So the large n limit, I think I kind of skip how we do the large n limit. So what we do is we take the SYK model, write down a path integral, do the average over the randomness. We get an 8 fermion model, and we bosonize this 8 fermion model in terms of bilinears of fermions, which in fact is the Green's function. And we implement this using Lagrange multipliers. If you do that, you find a simple result. So this integral is for the Lagrange multipliers, and this is because the psi integrals become G integrals. And the important thing is you find an action, and n only occurs in front of this action. And that means you can do the large n limit by saddle point approximation. So we can solve this system solving the saddle point equations, which are the Schwinger-Dyson equations. And at low temperature, you actually can, by inspection, you see that the left and the left-right Green's functions are related. And what you see is coming out are the retarded and the advanced Green's functions, which is kind of natural in the Keldysh formalism, because you always get the time-ordered Green's function out if things are on a contour. But I don't have time to go through the details. And I just show you the results. Here you see the Euclidean Green's functions. And there are two things we didn't see at finite n. Here you see only one slope. There's not a first strong slope and a much slower, lesser slope. And there are oscillations. This is the absolute value of the Green's function. That means here the function goes through zero. This is a logarithmic scale. And this is for small mu. For large mu, there are no more oscillations. And you find an exponential behavior for a very long range. So we see that the Green's functions decrease exponentially in a nice way. They go like e to the power minus gamma t times some cosine. Here the omega is equal to zero, and here it is not equal to zero. So the oscillations vanish when mu is larger than 0.05.
Gamma is a simple function of mu. I mean, it's therefore mu.
Gamma, yeah. I have gamma depends on mu, and also omega depends on mu.
Right.
And I have that on the next slide. So here there's gamma, and what you see is the same kind of behavior as I found for the first exponent, the short time exponent at finite n. Then there's a transition. And when we make the explicit coupling equal to zero, it is actually finite. It doesn't go away. There's oscillations. The oscillations go down at 0.15, which is exactly this point. So there's a phase transition here. And you see that also the character of the solution changes when you solve the Schwinger-Dyson equations. So this at low temperature, beta equal to 500, and so what we want to understand is the origin of these phase transitions and the origin of this anomalous dissipation when the coupling becomes small. If we compare this to the finite n case, and that's here, so this is again the solution of the Schwinger-Dyson equation. In fact, this is for n equal to in 1s by k is 9. There's really no need to do finite size scaling. It is obvious that if you would make n large, this curve would converge to that curve. However, this one from the long tail is not seen in the Schwinger-Dyson equations. That means that the Schwinger-Dyson equations do not see the exponent which follows from the spectrum, that is this for mu behavior when mu is small. It is not part of the Schwinger-Dyson equation. There's only this short time behavior. And if you look at these finite n results, if that's the black curve, there's a dotted curve. In the Green's function for different realizations has a complex phase. That means if you do average over many of them, you get a smaller result than when you just plot the average of the absolute value. So one possibility is that this behavior, because of the complex amplitude, actually gets averaged to zero at large n. And that is the best explanation we have. The other explanation is that we made a mistake, but we went to great length to check this. This result was obtained in two completely different ways by two different persons. At least one of those persons extremely reliable. there's clear.
So don't commit on who. We are on YouTube, so don't commit on who among the two persons is extremely reliable.
So they are both half reliable. So we don't know yet what causes this anomalous dissipation. One reason is it could be due to chaos because of the randomness of the complex eigenvalues. We actually have seen that before in a paper which was with Dario, when we looked at the pure non-Hermitian SYK, no coupling, just a single SYK, we actually found that the Green's functions decayed exponentially. And that might be exactly the reason here. So that means if you look at a model that has no chaos, this anomalous diffusion should go away. And we know a model without chaos, that is when Q is equal to Q2, it becomes integrable. And if it is due to chaos, then this anomalous dissipation should go away. And that's the last part which I'm showing. So the spectrum for Q equal to 2 looks very nice. So this is the ground state. We are spaced by mu. The real parts are spaced by exactly mu. And these are the imaginary parts. Clearly it is integrable. So the coupling term kind of is decoupled from the other term. If I compare to Q equal to 4, it's completely different. Look at this, the scale is the same. So Q makes it completely different. You see it is integrable. You can again solve the Schwinger-Dyson equations. In this case, you have the typical form. Also in the Q equal to 4 case, they look like that. But in this case, in Q equal to 4, there was a fourth power here. Here there's a first power. And that means they just become quadratic equations. And you can solve them analytically. The solution is simple. It goes like a Bessel function, which is oscillating. It's not exponential, K1. And there's an exponent, mu. And for the Q equal to 2 case, the distance between the ground state and the first excited state was exactly mu. So if you look at the analytics, you see that the relaxation rate goes exactly with mu, which is the difference between the first excited states and the ground state. And there are no further exponents. This is the only exponent. The rest is just some oscillatory and power-like behavior. And if you compare it to the solution of the Schwinger-Dyson equation, which are the points here, and this is the analytical result, you see that there's perfect agreement both for small mu after the phase transition and for large mu at the other side of the phase transition. In solving the Schwinger-Dyson equations, what you do going from Q equal to 4 to Q equal to 2 is basically nothing. You change a Q in your program from 4 to 2. And that also shows that the correctness of the Schwinger-Dyson equations.
So, because the solution that you gave before was also the solution of the Schwinger-Dyson, but analytical. Instead, now you are comparing
the analytical
code in which you assume that you don't know the analytical solution and you just remove the 4 and you put the 2.
Yeah, the red one is the analytical solution, and the black points, which you barely see, is a numerical solution.
But numerical for, I'm asking.
Of the Schwinger-Dyson equations, where we changed 4.
Exactly. So you assume that you don't know that because.
That's right.
Okay.
That's right. So the conclusion is that chaos is important.
And do you think, because Q equal to 2 is integrable, of course, but is single particle chaotic. So
Yeah.
you think you can see an effect of the single particleness?
There's a very almost no chaos. So Q equal to 2, I would call integrable. But
No, yeah, I know, but
you can see if you compare it, say, to Poisson statistics, you see the starting point of that. You also saw that in your paper.
Yeah.
It doesn't go, if you look at a form factor, it still goes down at some point.
Exactly.
And you can work it out analytically.
Right. But do you think that something here will depend on that or not? We did the large n limit. And in the large n limit, it goes away. At finite n, you see a random. Okay.
Okay, I will skip this, given the time. Okay, let me conclude. So what we have seen is an anomalous relaxation in a dissipative SYK model, which describes coupling to an environment. And it seems that the most important ingredient is that the environment is, that the model is chaotic, that you get very fast relaxation, even in the limit that the coupling is zero. What we feel doing is relating this anomalous relaxation to the spectrum of the operator. It's a puzzle. We thought a long time and hard about it. It delayed the paper by half a year, and we didn't find it. And we hope to come back to that in the future. But that's all.
Thank you for this nice talk. So we have still time for some questions, if there are.
So again, maybe this Lindblad operator mentioned that maybe or we are looking for the spectrum of data. So before this transition and after this transition, the first excited state, is there a change in the complex to real or real?
There is some change, but if you look at the spectrum figure here, for example, so this is the ground state. Here, that's the first excited state, and when at some point this first excited state becomes part of the cloud.
Yeah.
And we think that is related to this transition.
Okay.
So this is mu equal to 0.001, which is still quite some distance. The transition is at 0.15. But this becomes part of the cloud. And in particular, because previously in the paper with Dario, we found having just a cloud already gives exponential relaxation of the Green's function.
So if this is the case, then can it not be distinguished by the rigidity because this is the mixing of the one particular eigenvalue?
Yeah, but we would want more.
Okay.
Numerically, we found also at finite n, we found a number at 0.668 or something like that. Where is it? Oh no, it is here. Yeah, here. So this is 0.63. We want to calculate that 0.63 from the spectrum of the operator. And I cannot. It's a large number because the spectrum, if you look at the scale of the spectrum, this one goes between -1 and 1. So 0.63 is macroscopic. So it's hard to imagine it's related to a single spacing. It's too large.
Perhaps if I can have maybe a naive question. So is it any hope to have some experimental tests? Of this?
First of all, there are no naive questions. And experimental tests. I would say no. It's hard to, you can ask a more general question. Can you realize SYK model experimentally at all? There's some efforts, there's some condensed matter systems where maybe some part is realized. You can look at nuclear physics. It is the nuclear operator is almost a four-body operator. In nuclear physics, it's called a two-body operator. But there's also always a two-body operator as well. It's the sum of a four-body and a two-body operator. But the nuclear systems, they are not Majorana fermions. So they behave differently. There's no. Maybe you can measure relaxation. You actually can create a system, which is called a compound nucleus. You shoot with a neutron on a nucleus, and you can ask, how long does it take to equilibrate, or how long does it take that the system can decays? But this is a very much idealized model. In real life, you have to deal with real life things, like angular momentum, parity. So real life is much more complicated. So the SYK model is solvable because it has no structure. And real life models always have structure. If you have a quantum dot-like structure, then there's a lot of stuff going on, which is not part of this model. And it's very hard to distinguish the two. I still think that nuclei are still the best experimental model for the SYK model. The best experimental realization. There are a number of condensed matter papers with proposals to realize the SYK model. Maybe Dario knows that better.
Alexei is our local expert.
Well, just because I like that, that's the proposal with the normalizes Keldysh and Albert interaction. Space efficient structure.
Yeah, you mentioned that. And when no, you
Yeah.
discussed it with me. You
Yeah.
found the mean field equations of the SYK model from a simple Hubbard-like model,
Yes. Hubbard
atomic Hubbard model.
Hubbard.
But also Hubbard model is not an experimental model. It is not. It is also idealized.
Yeah, but nowadays we'll try call that an experiment, trying to explicitly the whole of politics.
And the Hermitage of suspended interaction is not range that would probably make things even better. Though it's more of a guess.
Yeah, of course, the N is large. And in real life, N is maybe not large. We have an all-to-all coupling and large. And that is exactly quite amazing that you get these equations for the Hubbard model, for a simple Hubbard model. So it is not a naive question at all. It's a very complicated question, but it would be nice if you just realize this model. But you cannot, because real systems are always more complicated.
Yes.
Yeah. Well, I'm just wondering, so this other field is missing large N equations. We try extract it by computing the log of the green function rather than the green function itself. To remove, well, I mean, it's the explanation of the complex phase that's,
to calculate it analytically.
Yeah.
To average the log of the function.
because it's.
Yeah, I would do like expansion kills the face. And but the Schwinger-Dyson equations are always intermediate. So you cannot do that. So you cannot, with the Schwinger-Dyson equations, you cannot calculate the absolute value of the switch.
Well, I was thinking of playing well,
You could introduce you double, yeah. You could introduce a complex replica, analyze the data. Which we tried in some sense. We didn't do that. It was not necessary because the models we looked at had eigenvalues that were complex conjugated. But that would be an interesting proposal to look at that moment.
Okay, any other questions from the audience? Seems not, so let us thank Professor Verbaarschot for the presentation.
Thank you.